Welcome to Spring LIB.
Okay, we are looking at the following molecule. We are going to look at it down from carbon 1 or carbon 2 to carbon 3. So let's consider what substituents we have on carbon 2. We've got a methyl, a hydrogen, and another methyl. And on carbon 3, we're going to have a hydrogen, and then this is going to be an ethyl, right? So we could draw this, for example, as ethyl, hydrogen, methyl, hydrogen. Okay, so now in the conformation that this is currently at, if we're looking down that axis, right, so I would expect methyl to be going to the right, up and to the right. I'd expect to have a hydrogen up and to the left, and I'd expect a methyl down below. Now for the back side, I would expect an ethyl to be straight up, and then to have hydrogens at the other positions. Now what we've got to do is identify the lowest energy conformation. What that means, and what we need to consider, is sterics. We don't want the ethyl and methyls to be next to each other if we can avoid it. That causes the energy to be higher. So what they're really asking is, what's the conformation that will have the least amount of methyls next to ethyls, right? So, for example, right now we have an interaction between one ethyl and a methyl, but all of our other interactions are between hydrogens and methyls, or methyls and hydrogens. So can we do better than this in terms of the ethyl and the methyl? Can we get an ethyl? Can we rotate this in some manner to get ethyl to not be next to a methyl, right? Well, in fact, we can rotate it. For example, if we rotate the front atom by, let's say, negative 120 degrees, we would end up with something like this. We'd have a methyl up and to the left, a methyl up and to the right, and a hydrogen down. We'd still have our ethyl in the back because we're not rotating that. Hydrogen here. This would be a worse or higher energy conformation because now we've got methyl next to ethyl and another methyl next to an ethyl. That's unfavorable. And so the last conformation we can consider would be to rotate it counterclockwise, 60 degrees. Right, so now this is going to move to there, this is going to move to there, this is going to move to there. Sorry, we just did that. We want clockwise now, 60 degrees. So this methyl is going to move down here. This will move up there, and this will move up there. This would provide us with a hydrogen here, a methyl here, a methyl here. And in the back, we would still have our ethyl pointing up and our hydrogens. All right, so we still have this interaction between a methyl and ethyl. It's just on the other side now. So of the three possible conformations we have where the bonds are staggered, these two are the lowest energy, and they're equally low energy. This would be the highest energy. Now, there is one other option that could be worth considering. In each of these cases, we've drawn the bonds being staggered. That is, if we were to, for example, rotate Newman projection like this instead of a whole 120 degrees, should have said 120 there, instead of 60 degrees, what we'd end up with is the following. Right, we'd be overlapping the functional groups. So we could end up with something like a methyl here, a methyl here, and a hydrogen here, and then an ethyl here, a hydrogen here, and a hydrogen here. Now this is very unstable because these methyl and ethyl are as close as they can be. So this is the least stable staggered conformation, but this is going to be the least, the highest energy conformation possible, and this is eclipsing. So this is an eclipsing conformation, whereas these are staggered. So the answer to this question depends on whether you should give a staggered conformation or an eclipsing. Eclipsing are often ignored because they're so unstable that the molecule will spend very little time in this eclipsing conformation.